So, welcome back and welcome new people. It's again a great pleasure for me to introduce a speaker, an invited guest we have here today, Professor Luis Almeida from University of Porto. And he's the flexible guy. When I met Luis first time, it was many years back. We're talking about 25 years back.
More.
No, it was 2000. If you were in London, I think you were. Yeah. So, yeah, we're getting old. But the topic at the time, so this talk will be about real-time systems, and you know real-time systems is something that's always predictable, but Luis' special flavor has always been, can't we be a bit flexible and you know, introduce some dynamic features into our strict timing critical systems. You can read more about Luis's bio in the material provided, but very shortly, so he's professor at the University of Porto, and he's a very central figure, I would say, in the IES Technical Committee Factor Automation related conferences, but also IEEE Technical Committee on Real-Time Systems community. So it's a great pleasure for me to introduce Luis Almeida and blast us away with a flexible thought on real-time flexible systems.
Thank you. Thank you very much, Thomas. Thank you for the very nice and kind words. You know, I started liking, you know, the flexibility topic when I started, you know, having to you know, take trains and commuting, and then I said, why can't it be flexible, you know? Every time I was missing one, I mean...
Oh, sorry, I made a mess.
And now we are adjusting, and you see why flexibility is important.
Okay.
Okay.
Is it okay?
Yes. All right. So, I know, you know, Alessandro was spoiling my first joke. You know, that's me in my previous life. Exactly, that's true. Maybe in my next life as well, I don't know, but definitely not in my current life. But anyway, a little bit about flexibility. So, I think, you know, I was thinking about which topic, and it actually fits very well with the PhD that we'll have in the afternoon. And I didn't know about Thilu's talk, but it actually fits well with Thilu's talk as well, because it's a different perspective. In some way, let me start by a comment with respect to the last question that Thomas asked. You know, we have factories that can last, you know, decades. But the fact is that there is probably no more a factory that will last decades doing the same thing. That's probably over. That's probably over. And we probably want our factories to be doing different things all the time. And we've had that, for example, during the pandemic, in which we had factories being, you know, converted to one day to the next produce masks and produce this alcohol, gel, and whatever, and things that were needed, right? And that's going to happen more and more for whatever the reasons. Anyway, so and also it's also interesting with respect to safety and security, because flexibility has been rejected, you know, very clearly from the safe point of view and also secure point of view in some way. But the fact is that when we build systems that are safe, most of the times we are already incorporating inside the system some level of flexibility. And at the end of the day, what makes them flexible, what makes them safe is actually the flexibility that they have inside. For example, fault tolerance by having, you know, components that replace other components. So the function seen from outside is the same, but it's the same at the expense of changes and adaptations that are done inside. Which is, you know, an interesting point of view. Anyway, my case today, and what I would like to do, is to make a case for flexibility in this, let's say, real-time embedded systems. And real-time embedded systems has been one of those domains in which flexibility has also been seen, as something, hard, because it reduces the knowledge that you have a priori to design your system. But in fact, when we see as flexibility as the concept has evolved and how it was taken by other, communities and by other domains, then we see that at some point this will end. And there are this resistance, and there are some, signs that it's happening now. And for example, one of the signs is exactly, the PhD talk that we will see this afternoon in industry. So there is interest in using the flexibility of IT technologies and tools to improve, some properties of the operations domain. In this case, safety, for example, as well. But what I will do is the slides are not nice, so I apologize, and they even look worse after Dilu's talk, so I'm sorry. Double apology. And then a third apology to Mohammed, because a previous version of this talk was, I used it in June in WFCS, and I planned it very poorly, and I overran the time, and it was an incredible thing. And Mohammed just showed me the 5 minutes, then the 2 minutes, and said, well, I have to, 0 minutes. I said, damn, I have to finish, -1 minute. And then at some point, a skull, and I'd never seen that. So it was the first time in my life that I saw someone showing me a skull, But it was, I deserved it. I deserved it. So my public apologies to Mohammed because of this very bad, planned talk. Anyway, let's go through it. All right, so several, here, no? Page down? No. Oh. Okay, I have to click on the presentation, yeah.
Sorry.
It's here.
Oh, yes.
That's it. Good, very good, very good. All right, so, no, oops, came back. All right, yes. So a bit about flexibility. And I don't want you to read all these, but there are some highlighted keywords that I want you to see. And I will draw your attention. So flexibility has been viewed as and studied as a physical property, an attribute of decision making, an economic indicator, strategic tool. At least 50 terms exist for various types of flexibility. This is a quote from a paper from 22 years ago by someone that used to do a lot of research on the topic at the time and was doing an ontology on flexibility, essentially to the manufacturing domain, but more or less in general. And then it was very interesting to see that flexibility, there were several, let's say, statements that were taken from there. So one of them is that to be employed in a realistic manner should result in little penalty, so the overhead must be minimal. The best possible performance, functional richness, and in manufacturing, ability of the system to adapt itself to various changes, and this comes from 82. So far, not now, not now. So more than 40 years ago. Anyway, so types of, one of the things that we saw then was that there were many different types of flexibility, particularly in manufacturing, in those studies that I was showing you. And this comes from 84, and they were discussing at the time flexible manufacturing. So flexible manufacturing is a concept that is at least 40 years old, right? And this was probably a hype at the time. And it was, I think it's impressive that it lasted so many years. But the interesting thing here is that I identified a lot of different types of flexibility. And this makes all sense. Because when we say, oh, my system is flexible, flexible with respect to what? What is, maybe flexible because it allows you to change, the processor that is running a function because of a fault tolerance issue. Or maybe it is flexible because it allows to adapt, the resources that it's taking, like, for example, reducing the rate at which it runs a certain activity, or maybe it is flexible because of some other, whatever, some other dimension. And so, just to say that there were a lot of different dimensions that were identified at the time. Now, looking at another domain in which flexibility has been, really considered is systems engineering. And there are some interesting statements also from the same time, more or less in the beginning of the 2000s. And there's this very interesting statement. Flexibility, however, is a word rich of ambiguity, exactly because of the multiple facets. While it is being increasingly used in various fields, few attempts have been made to formally define and quantify and propose ways to achieving. This is very important because I think it's one of the reasons why it hasn't been more widely applied, for example, in embedded systems or in real-time embedded systems, because we haven't quantified exactly, we haven't formally defined what we, understand as flexibility. And that has been very important. So flexibility, despite its popularity, is not yet an academically mature concept, and this was from 2009. So compared with other concepts. So flexibility is recognized as a critical attribute of a system, a process, organization. It is needed to cope with uncertainty and change, and implies an ability to change and adapt to a range of conditions. This is, I think, very important. Now, we can also see flexibility as a way of adding value to your system. And there are some interesting statements, these are not that old, from 2011, that and in particular, this is, I think, interesting, the first one on top. So it says that designers of complex, long-lasting projects, such as communication networks, power plants, hospitals, must learn to abandon fixed specifications. This is very important because it draws our attention to evolving requirements, to specifications that are not static during the lifetime of your system. They are going to change while your system is operating. And this is very important. And then they say there that if you plan to average, you're most likely underperform, because it will be either too good or too bad. But if you plan for average, it will not be adapted to any of the circumstances. So flexibility contributes to improved economic value, sustainability, and resilience by enabling systems to adapt and reconfigure in the face of uncertainty. So I think this is the main message that I wanted to convey here. And this is from 2022. So this is more recent statement. All right. In software development, I think it's well known that flexibility has been taken as something that is fundamental. Agile methods are all based in flexibility, and modular designs, configuration management, all these feedback loops with all the stakeholders, in the development. And then all these parts that are important to make your software development flexible, iterative development, the containerization, collaboration, clear documentation, modular architecture. So this is basically the same thing. So in software development, we do follow flexibility in different aspects. Now, in embedded systems itself, it's interesting, these are very recent statements, and I took these statements from, magazines. So that one is online. This is from Software Development Times. And that one, it says that the hurdles of embedded systems concerning robust and flexible designs are related to the limited resources, the monolithic philosophy driven by a need for ultra customization. This is one of the characteristic features of embedded systems. And a diversity of components as well makes the overall system complex. And so the development of embedded systems may be made more flexible and adaptive, as well as more effective and resource efficient by leveraging microservices architecture and continuous integration, continuous development. So this is just for us to see that the whole idea of flexibility in the software development is migrating to embedded systems as well in some way, right? So they are already saying that in order to make them more flexible, we need to leverage microservices, which basically boils down to also containerization and this kind of tools from the IT domain. So also other let's say tools that we see, the foremost advantage of a software-defined approach, and this brings us to the software-defined wave that we see nowadays. In embedded devices lies in adopting an agile process where a product can iterate and evolve quickly and its features can augment seamlessly post-production. So software containerization facilitates faster application and development and deployment, coupled with heightened portability and flexibility. So this is, again, just to show that there are motivations, strong reasons to adopt flexible approaches, not only in the development, but putting flexibility in the operation of your system to adapt to resources and use resources more efficiently and adapt to circumstances that are not known. And this is something that we knew before, and we were working already for a while in this direction. There was a period from 2008 to 2015 in which we organized this workshop, APRES, so Adaptive and Reconfigurable Embedded Systems. And I just take this quote from the motivation. So it was said that the system is said to be adaptive in response to environmental changes, resource changes, or non-continual feature usage in ways that extend the space of operation and improve efficiency in the use of system resources. But designing and developing adaptive systems raises a number of challenges, and this is the point, right? From modeling and analysis to testing, including the need to deal with trade-offs between added complexity and achieved efficiency. So it doesn't come for free. There's no free lunch. And now I recall the first, comment about the need to have very low overhead. If we don't manage to have low overhead, then it's purposeless because we will pay more to have flexibility than the benefits we will extract from it, right? Anyway, it's always something that we have to consider. Now, this quote, I think I like it very much because it was stated at the time. This was a keynote of the APRES workshop in 2011 by John Knight, which is a well-known researcher in dependability, right? In dependability. And he was working a lot with the aviation industry. And he was saying that the complexity of modern embedded systems has reached the point in 2011 where adaptation in response to change during operation has become an essential design requirement. So he was advocating this in 2011, right? And so this is just to say that the motivations were there already at that time. Okay, and now I'm going to drive you through several results that were, developed along the years, that were all of them contributing to flexibility in embedded systems, and particularly in real-time embedded systems. So one of the approaches that was, probably easy is to have a system with multiple configurations and then encoding configurations in a very compact and efficient way so that for the lifetime of your system, it can go through different scenarios and then change configurations, and that same, let's say, design that was developed or made in the beginning can cope with all the different scenarios. So there were just two examples that I show here. So the first one was a work by Ian Bate and Paul Emberson that I was just commenting with Sasi before. But it's interesting to see the quote that I picked from their paper there. So changes arise from maintenance, enhancements, and upgrades. And the flexible design will allow tasks to be added without impinging on other tasks. So at runtime, we may be able to add tasks and being sure that they will not cause other tasks to fail, at least not even to fail their deadlines. And this was also another interesting work at the time by Sebastian Fischmeister that was also part of the group that was organizing the APRES workshop. But this was even before those workshops. And he developed a way of, you have a TDMA cycle but allowing a TDMA cycle to be flexible, because depending on what was happening, maybe the cycle was not going through to the end and could, reset in the middle. And so it was an adaptive TDMA cycle in some way. So there were different configurations of the TDMA cycle that were already encoded in the TDMA cycle. And this was called the tree schedules. It was an interesting work at the time. Now, flexibility can also be used as a way of providing graceful degradation. This has been also very well known. It has been used, for example, to cope with overloads. And there are two very well known, actually three, because the third one I think that we can include it in this category as well. These skips, so managing overloads with skips. This means that when you have an overload, you skip some activations of some tasks, right? And then you can prove that the system with these skips is still schedulable, and you still keep the timeliness of a core set of tasks that you want. And then you also have this MK-firm model, which is also very well known, which allows you to skip, K minus M every K activations. And you still have the guarantee that with those M activations within K, you can keep the system working. And then this mixed criticality framework that generated such a hype in the last, let's say, 10 years or so. In fact, it also comes from this approach. It's you have tasks that can have an execution time that can sometimes be longer than what is considered common. And this is on purpose, because if they consider a very conservative upper bound for the execution time, then the system will be very inefficient. But this will happen only occasionally. So what they do is that, okay, I will consider a lower upper bound for the execution time, but I have a higher probability that it will be overrun. When it is overrun, I change the mode of my system to a higher criticality, which basically means that this task is going to grab resources and prevent other tasks that are non-critical from executing. So again, this is flexibility. And this is for some kind of graceful degradation. So now, flexibility also, it was very much used for dynamic quality of service management. This was one of the reasons to use flexibility as well. And I remember this from the late 90s, this framework developed at CMU, the QRAM, so the QoS Aware Resource Allocation Model. That was a framework that allowed to include multiple different operation modes of applications that were using multiple resources. And so depending on the state of occupation of the resources, then the applications would be operating in different quality of service levels. And in this way, they would show, or they could show, that they would maximize the quality of service level of a group of applications by adapting to the resources that were available at runtime. This was just one experiment. And then another work that was instrumental in flexibility was the elastic model that was, in fact, proposing a way of adjusting the rates at which tasks execute. And each task could be, maybe with a fixed rate, maybe with a range between a minimum and a maximum, maybe a range between, 0 and the maximum, and within this range, maybe adapting easily or adapting with resistance, right? So with an elastic coefficient. This was a very interesting, model that was used, in several different ways. So one interesting approach that allowed it to be used in distributed systems, and I'm very proud of that. It was the first approach that allowed to do any kind of scheduling in a distributed system, was this that we call the flexible time-triggered communications, because it provides a centralized scheduling and triggering of communications in a distributed system. And this way, we could put in the master any scheduling on the fly, adapted, changing the way that we wanted, and we could do and show elastic scheduling on flows, streams on a shared link, communication link. Now, at the time, I was advocating that we should evolve in the way of expressing our requirements. And our communication requirements in particular, and this is what I was looking at the time, we should express them in a way that I could have different possible rates. So influenced by the elastic model. So having the elastic model in mind, but not necessarily adapting in an elastic way. It could just be discrete changes between the high mode and the low mode, between maybe, off, on, maybe between off, on, and the high mode, if resources are available. And then setting a criticality, dimension to allow you to, in an easy way or a fast way, knowing who should get the resources that are freed first and who should release the resources when they are needed, right? And so this was, let's say, an easy way to manage this in embedded systems. And basically, one thing that became very important was what we call the QS management policy. The QS management policy is the rule by which you change configurations at runtime. And they are all runtime configurations. And we were doing this, generating the configurations at runtime. They were not expanded configurations that were all encoded in the system. No, they were configurations that were generated at runtime. Now, one very important aspect was that the whole space of configurations contained non-valid configurations. So the subspace of valid configurations was just, this bluish area. But within that part, most of the times our tools to detect whether an online generated configuration is acceptable or not, most of the times they are pessimistic. And so we would end up with a smaller subset with this, which is this green area, right? And within the green area, because we are changing, at some point from configuration A to a configuration B, if the configuration B is inside that space, fine. But sometimes it can happen that the QS management policy pushes you back outside that area. And in that case, you are stuck because you cannot stay in the same configuration. You have to change to a different configuration that is not valid. What shall you do? And what we were advocating at the time was that we should have what we were calling a nominal configuration, which is a safe configuration by design to which the system falls back in case there is no safe configuration available at the time of change, right? So this was something that we were proposing at the time. And with these ideas, we became convinced that we could actually propose, systems that could be, verified, that could be verified and guaranteed to have the minimum resources to operate at the safe level, but if resources are available, operate at a higher quality of service levels. And so we were advocating at the time, in this particular case of scheduling multiple virtual machines inside a multi-core CPU, and we were advocating that we could even certify, and this would be certifiable because we could first guarantee minimum bandwidth to every critical virtual machine, and we could prove that they were isolated from overruns. And then we had what we call dynamic slack arriving from idling in the virtual machines when the operating systems were idling. Then this would release resources that could be distributed using the elastic task model. And we had a very fast and efficient way of allocating these extra resources. And so we were advocating that this could even be, certified at the time. Now, there were other works, and this is, one of those paradigmatic works that has to be mentioned in this topic. It's the work of the simplex architecture that was proposed by the group of Louis Cha. And what they were doing at the time was to do, let's take a system perspective, not just a software perspective of tasks that are executing in CPUs. Let's have a hardware-software co-design approach. And why this? Because if I want to tolerate bugs in my application, but also bugs in a complex operating system, right? I need to have a fallback that is not in the software domain, right? And so what they were doing was that they were proposing to have, for example, in the particular case of controllers, they could have what they call the safe controller implemented in hardware that would provide minimum performance, and they would have another controller that would be, a more powerful controller that would provide very good performance, but it was not guaranteed. It couldn't be certified because of extra complexity, because the operating system was too complex, because the application, the controller was too complex and couldn't be certified. So in this case, the application would take advantage of the extra performance while everything was working fine. If something happened, out of the specification because of some bug, whatever the circumstances, it would fall back to a safe controller designed in a totally independent manner that would keep the system operating. So this was, interesting and still another dimension of flexibility. Now, as we approach, these last years, we see, and we've heard in the morning, and we will see even more in the afternoon, we see these IT tools that have, inherent flexibility that come from those agile methods and that come from this, resource optimization. And they are entering the distributed embedded systems domain. And in particular, software-defined networking is a disruptive networking paradigm. This is something that we were writing in a paper in 2017. But although it emerged from campus networks, it was soon considered for use at industrial level because of the capacity that it has to control the different flows and to do flow-based control in a system. Now, it turns out that we were providing at the time hardware that was more capable than common hardware. Hardware that could, for example, provide real-time channels in hardware. For example, Ethernet switches that were capable of providing, specific per flow shapers, per flow, not per class, per flow shapers. And there was no way of configuring them in a standard fashion. It had to be our own tool, which was not. And so what we did at the time was to extend OpenFlow and to show that it was easy to extend OpenFlow to program from the controller those shapers online, right? And so this is something that we could do by bringing in the flexibility of these IT tools. And now finally, just a word to say that we feel that the industry is picking up on this and is now becoming more receptive. And we just looking at this software-defined paradigm, and if we look, for example, at the automotive domain, there's nowadays a hype with what is called the software-defined vehicle. And the idea of the software-defined vehicle is to be able to manage the vehicle software as what we call a service-oriented architecture, basically, where you deploy services and where you deploy applications that will then use the services, and then you will have to rely on containerization, and so you will have probably containers that will be managed with a certain framework, probably Kubernetes or something like this, or modified to have real-time properties or real-time capabilities. So this is important. It says there, that SDV represents a major technological advance. It revolutionizes the driving experience by fully exploiting the technological potential of the car through updates and introduction of new functions throughout the vehicle's lifetime. So once again, it's not only the factories that will have to be reconfigured during lifetime, vehicles will be reconfigured during lifetime. Why? Because there will be software updates, because there will be, these driving assistance systems that will be constantly, bringing new functionality, because the vehicles will be autonomous and there will be updates because they will be safer, or they will come up with a certain feature that will allow the vehicle to, dance and jump and do whatever, and people will want to do this, right? Maybe not dancing, but, adapting to different driving styles and different conditions. So we don't know, right? But this is definitely a trend at the moment. And just bringing this up, that there's currently one of these, political, European projects to push, these things, which is called this shift to SDV, which is gathering 80 partners. So it's one of these big things, which essentially is there just to create energy in this direction. And so I think that this will really happen. All right, so wrapping up. Flexibility is a powerful property embraced by several industries, in particular the software development industry, but also systems engineering and also manufacturing. And it enhances efficiency in using resources, reduces costs, improves robustness and lifetime. Flexibility in real-time embedded systems still lags behind, probably because many of these embedded systems are safety critical, and there's this focus on absolute worst-case conditions, and this somehow hinders, flexible approaches. But the fact is that we have all that is needed to deploy different kinds of flexibility in our system. Many techniques that have been developed over the last 20 years. So I wouldn't say that we have all, but we have a lot, right, of what is needed. So it's not really a technological issue. It's really an issue of deciding that it's beneficial, right? And that's the issue. That's showing that it's beneficial. Now, the industry seems to be more receptive now, and this is basically what is to be done, and what I would really like to contribute to, and to motivate you to contribute to this is really, we need to define a flexibility ontology in real-time embedded systems to show what it is, its different facets, its types of flexibility, and essentially try to define it formally in some way for each different type of flexibility, and quantify the concept, the benefits, and the costs, because this is the way of showing that, no, we are going to, take benefit from using this. But, all the costs must be there. The costs of the flexible mechanisms, the costs of, whatever, the reliability, the costs of, also the costs of security. And this is just the last line in there because I hadn't mentioned it before. And, it connects well. The slides were already done, so I didn't edit them. This is just but it's definitely important, right? I think it's very important because, flexibility enlarges the attack surface anyway. So this has to go into the costs, and it has to be, balanced according or against the benefits, right? And when the benefits, outweigh the costs, then there's no reason not to use it. And I think then industry will embrace it, right? And that's my take. All right, thank you very much for your attention.